Hi, Year 12. It is time to talk about quantitative electrolysis. So today you're going to need your booklet and you're going to need a pen or pencil and your calculator. So let's get the whiteboard on and let's get started. Okay, so we are looking at your booklet today and we are looking at page 27. So find that in your booklet. And today we're going to talk about how you calculate the number of moles of electrons that's flowing in an electrolysis circuit. So for this we need to learn about a couple of laws. First one is Faraday's first law of electrolysis, which says that the amount of any substance that's deposited, dissolved or evolved in an electrode during electrolysis is directly proportional to the quantity of charge passing through the cell. So by amount here, we actually mean moles. Okay, so amount always means moles. And charge is measured in coulombs. So some of you have not done electricity to the point where you've looked at charge. It's measured in the units of coulombs. Current is measured in amps, and time for this is always in seconds. So you've got to be really careful that you always convert time to seconds. All right, so if we can work out the charge, it's Q equals IT, so the charge is equal to the current multiplied by the time. And so what, you might say? Well, the interesting thing is that we know we have chemical data that tells us what the charge on an electron is. So the charge on an electron is 1.602 times 10 to the minus 19 coulombs. That's just data, and you can look that up to as many significant figures as you need. But the interesting thing about that is if we know the charge on one electron, we can work out the charge on a mole of electrons just by multiplying by the Avogadro number. And that charge comes out to be 96,500 coulombs. And that is known as the Faraday constant. So for 1 Faraday, or the Faraday constant, you'll always be given the Faraday constant in exams. You don't have to memorize it, although after a few examples you'll probably know it. So if Faraday's second law of electrolysis says that if you want to produce 1 mole of substance by electrolysis, you've got to have a whole number of moles of electrons being used up. So you can't have 1 mole of substance being produced by 0.5 moles of electrons. It has to be a whole number. All right, you can put those two can actually work out the number of moles of electrons. If you know the charge and you know the charge on a mole of electrons, then you can work out the number of moles by just charge divided by the Faraday constant. So putting those two formulae together, if we've got Q equals IT and moles of electrons is equal to Q on F, then moles of electrons must be equal to IT, which is our Q, on F. And most of the problems that you do in this particular topic involve finding out what the moles of electrons are as part of their working out. So you've got 3 types of questions. Okay, the first type is where you're given the electrical data, so you're given the current and the time, and you have to find the mass of the substance produced at the electrode. So you're given electrical data, and you need to find the mass of a substance formed. Or it might be the mass of the substance that missing from electrode as well. Whoa, where are we? Okay, so usually the questions are the mass of a substance deposited at an electrode. I don't know why that's not working. Oh dear. Here we go again. I promised I'd learn this technology. All right, so that's the first type of question. The second type is where you're given the mass of the product and you have to find some aspect of the electrical data. And then the third type, the really nasty type of question that we can ask you, is the one where we give you the electrical data and we give you the mass of the product, and you've got to work into the middle to work out the charge on an ion. Okay, so that's the three kinds of question that you can expect from this. And of course, I have an example of each type in our working. And generally though, let's look at the fact that generally, you're always going to have to find the moles of electrons. In all of this, you always have to find the moles of electrons. And that might be from electrical data. It might be from the moles of substance, then a mole ratio. But with all of these, you're always going to have to find the moles of electrons. You are going to need to then use a mole ratio. And then you're going to need to convert to either mass or electrical data. So that's your basic steps that you need to go through. We always need to start with, our starting point is always our balanced half equation. So that's always where we're going to start. Let's have a look at the examples in your book. So our first one is one of the first type. You're given electrical data. You're given a current of 2.00 amps. So that's our current. And it's passed for 2 hours. And oh man, I haven't changed this again. Let's get rid of that 2 and call it 2.0 because we don't want to be cut down to one significant figure. So let's makes no difference other than significant figures. Through an electrolytic cell containing copper electrodes in a solution of copper 2 sulfate. All right, so first thing we need to do is get our balanced half equation. So if copper is being deposited on the cathode, we're looking at copper ions reacting with gaining 2 electrons to produce metallic copper. So it's in solution, so this is aqueous, and this is our solid copper forming on the electrode, just like we saw in our practical video the other day. Then we need to look at working out the moles of electrons. So in this case, we've got electrical data, so we're going to work out the moles of electrons by IT on F. So I, our current, is 2.00. We're going to multiply that by 2 hours. Remember, that's got to convert to seconds though. So 2 hours times 60 minutes times 60 seconds. And then we're going to divide that. Let's just get rid of that. Go back to that. And we're going to divide that by the Faraday constant, which is 96,500. So plug and plug that, and you get to 2 significant figures, 0.15 moles. All right, now when asked to find the number of moles of copper, and we can, in our equation here, see that we have a mole ratio of 2:1 for our moles of copper. So moles of copper over moles of electrons is equal to 1/2. So therefore, our moles of copper is going to be half of our moles of electrons. And keeping the original answer in your calculator, you do get 7.5 times 10 to the minus 2 moles of copper. Now that you've got the moles of copper, you can easily convert that to mass simply by multiplying by the molar mass of copper. So mass of copper is equal to moles times by molar mass, which is 7.5 times 10 to the minus 2 times by 63.55. And that comes out to, plug and chug with your calculator, 4.7 grams. Okay, so that's the first kind of question, where you start with the electrical data and you'll work your way through to the mass data. The second example is going backwards. You're given the mass data and you've got to go back to the electrical data. So example 2, 4.8 grams of copper, well, I didn't make that very different to the first one, did I? Is deposited at the cathode during the electrolysis of copper-2 sulfate solution with copper electrodes for 1.5 hours. What is the magnitude of the current? So here we're being asked to find I, which is our current. And we're being given the mass of copper. So let's convert that to moles first up. Always, if you can do nothing else in any of these questions, just convert to moles. So moles of copper is equal to mass over molar mass. Mass is 4.8 and the molar mass is 63.55. So the number of moles of copper comes out to be 7.6 times 10 to the minus 2. Right, now to find the moles of electrons, we just use that mole ratio from the equation. So our moles of electrons over our moles of copper, remember always put your unknown on the top, is equal to 2/1. So the moles of electrons will be equal to double the moles of copper, which comes out to be, not surprisingly, 0.15 moles. Now we need to convert back to the electrical data. So our moles of electrons is equal to IT on F. So if I want I, That's moles of electrons times by F over T. Moles of electrons was 0.15. Faraday constant's 96,500. And our time in the question was 1.5 hours. That's 1.5 times 60 times 60. And plug that through the calculator. And you get 8.1 amps. It's for a long time. I mean, 1.5 hours running that current is only going to give you 4.8 grams of copper. So you can imagine on an industrial scale what sort of currents they're going to need to use to produce copper on an industrial scale. That's huge. All right, one for you to try. Now, you've got to try not to be tricked here, because we are asking you to look at molten magnesium chloride. Now, this is actually easier than an aqueous solution. It's just that for some reason, because we just briefly mentioned molten salts at the start, often when you get a molten salt question, you just sort of go, huh, what? But in this case, it's very easy. Okay, so remember, anions. Anions go to the anode and they get turned into their element. And cations go to the cathode and they get turned into their element. So at the anode, our anions are the chloride ion here. And our cations are the magnesium ion. All right, how many grams of magnesium metal can be produced by passing 0.425 amps for 1.5 hours? I want you to have a go. This is just like the first question. This is a given the electrical data, find the mass data. So pause the video and have a go at that question. No, like really have a go. Okay, so you've looked at the electrical data, and our electrical data equation is moles of electrons is equal to IT on F. And your current is 0.425 amps. And your time is 1.50 hours. When you times 60 and times 60 again, that's not going to limit you to two significant figures, because if you're working out the number of seconds in an hour, it can be as many as you need. There are many significant figures as you need. And then that is over our Faraday constant, 96,500. And if you chug that through the calculator, you'll get 2.38. At least I hope you will. This is what I'm getting. Times 10 to the minus 2 moles of electrons. Now we apply our mole ratio to get our moles of magnesium. So moles of magnesium over moles of electrons is 1 over 2 from the equation up here. You can see we have 1 magnesium and 2 electrons. So there's our mole ratio. And so our moles of magnesium is going to be half of our moles of electrons, which comes to 1.19 times by 10 to the minus 2 moles. And then to convert that to our mass data, mass is equal to moles times bimolar mass. 1.19 times 10 to the minus 2 times by magnesium is 24.31, which comes out to be not even a gram, 0.289 of a gram. So you can see industrially, to produce magnesium chloride to produce magnesium from magnesium chloride, you're going to have to use a much larger current than that to get a significant amount produced. All right, how'd you go? Did you get that one? Final type of question, the nasty. This is the one where we really find out who knows their stuff. This is where you are asked to find the charge on an ion when you're given some electrical data and some mass data. This is, instead of working, the first example, we sort of worked from the electrical data through to the mass data. In the second one, we went from the mass data back to the electrical data. This one, we start at each end and kind of work into the middle. So first things first, platinum is a metal. Just in case you didn't know platinum was a metal. Metallic platinum tends to give it away, but just in case. So that means it's going to have positively charged ions. Which we also know as cations. And that means that they're going to be attracted to the negative cathode. We don't know what their charge is, so let's let it be X. Okay, so let the charge be X. Platinum is a transition metal, so it can have variable charge. So let's let the charge be X. So we're talking about PT X plus. If we're going to write the half equation that's occurring at the cathode, then our platinum X pluses are going to gain X electrons to make platinum. So that's going to be our cathode half reaction. And here's the interesting thing, this is how we're going to find X. Our moles of electrons over our moles of platinum is going to be X over 1. So what we're going to do is, for our moles of electrons, we're going to use the electrical data. For our moles of platinum, we're going to use the mass data. And then by taking the ratio, we'll work out what the value of X is. So let's give it a go. So moles of electrons is equal to IT on F. We've got 2.50 as our current, 2.00 hours times 60 for seconds, over the Faraday constant, which is 96,500, and that comes out to 0.187 moles. Then we will find our moles of platinum from the fact that we have 9.09 grams over the molar mass of platinum, which, if you look it up, is 195.09. So that's 0.0466 moles. So all we've got to do to find the charge on the platinum ion now is to take that ratio that we spoke about before. So that ratio was moles of electrons over moles of platinum, which is 0.187 over 0.0466. So it comes out to be 4.00. And that means that X is 4.00. 0.00. So our platinum ion is 4+. That is the types of questions that you're going to be asked on quantitative electrolysis. What I want you to do now is have a go at the worksheet questions, and I will see you in the next video.